In the previous lectures, we talked about the line element for various spaces. So the line element is defined as ds squared is the distance between nearby points squared. What about space-time? Okay, first of all, what do we even mean by points in space-time? A point in space-time is an event. So it's something that happens at a particular spatial location at a particular time. For example, if you clap your hands together, that hand clap occurs at a particular place in space and at a particular time. That's referred to as an event. So the interpretation of the line element for space-time is a little bit more complicated than it is for space. In the case of space-time, ds squared can be either positive, negative, or zero. Okay, and the interpretation in each of these three cases has to be handled separately. So let's first start out with the interpretation of the line element ds squared when it's positive. So if ds squared is greater than 0. Okay, in this case, the meaning of ds squared is it's the spatial separation between events or points in space-time. Spatial separation between events as measured by an observer who sees those events as occurring at the same time. So the observer sees the events as being simultaneous. Squared. Okay, so that spatial separation squared is the meaning of ds squared. So in short, we refer to this spatial separation as measured by an observer who sees the events as being simultaneous. We refer to that as the proper distance. So this is the proper distance squared. Okay, and of course ds itself is then just the proper distance. Okay, in this case, when ds squared is greater than 0, we say that the two events in question are spacelike separated. All right, now, next case, what if ds squared is negative? All right, in this case, we interpret ds squared as minus the following quantity squared. It's the separation in time between these events, nearby events, as measured by an observer who sees these two events as occurring at the same spatial location. And we square that. Okay, in this case, we can define what we call d tau squared as minus ds squared. So it's just the quantity in parentheses squared here, so without the minus sign. And d tau is referred to as the proper time. So d tau is the quantity that's in parentheses here. This is referred to as the proper time between events. So it's the time between the events as measured by an observer who sees those events as occurring at the same spatial location. In this case, again, where ds squared is negative, we refer to the two events as being time-like separated. All right, the third case is the case in which ds squared is 0. Okay, in this case, the separation between the two events is referred to as light-like or null. Light-like separated or null. In this case, the two events can be connected by a light ray. And of course, the light ray travels at the speed of light. Let me make a side comment about units. In relativity, we often measure both spatial intervals and time intervals in common units, for example, meters. So both space and time intervals in, say, meters. Okay, and what that means is, well, we know what a meter of spatial distance means. A meter of time means it's the amount of time that it takes light to travel 1 meter. So in these units, where we're measuring both space and time in meters, the speed of light is just equal to 1. So 1 meter of space per 1 meter of time. And in more traditional units, 1 meter of time would be 1 meter divided by c, which is 1 meter divided by 3 times 10 to the 8th meters per second, which is 0.33 times 10 to the minus 8 seconds. So that's, what, 3 nanoseconds. So now let's continue talking about the interpretation of the line element for space-times. And let's use a simple example. The most simple example of the space-time is the line element that describes space-time without any massive bodies. So this space-time is flat, no curvature. To use Newtonian language, no gravitational fields. All right, this space-time is the space-time of special relativity. All right, we can write the line element for this space-time in what are referred to as Minkowski coordinates. Which are usually given the symbols t, x, y, and z. The line element is ds squared equals minus dt squared plus dx squared plus dy squared plus dz squared. Now, we need to be careful here. We shouldn't assume, because we're using familiar symbols, t, x, y, and z, that these coordinates have any particular physical meaning. They're simply labels for events in space-time. So these label points or events in space-time and do not necessarily have any particular physical meaning. Okay, so for example, I could have just as well written this line element in terms of coordinates, say alpha, beta, gamma, sigma. All right, and this would represent the same space-time, the same geometry. Okay, now we can also use, not only can we change the labels for the coordinates, we can change coordinates as well. So let me give you another coordinate system, which is referred to as Rendler coordinates. Okay, Rendler coordinates are related to the Minkowski coordinates, and I'll go ahead and use Tx, y, z for the Minkowski coordinates. Rendler coordinates are related to Minkowski coordinates in the following way. T is, we'll call the coordinates rho, tau, xi, and zeta. Okay, so this is rho times hyperbolic sine of tau. X is rho times hyperbolic cosine of tau. Y is unchanged, but let's call it, give it a new name, call it xi. And z is unchanged, but let's give it a new name, call it zeta. Okay, so Rendler coordinates, tau, rho, xi, and zeta. And we can work out the line element in terms of these coordinates. So how do we do that? We just need to compute dt, dx, dy, dz, and then we can plug it into the line element in Minkowski coordinates to convert it to Rendler coordinates. So first let's compute dt. That would be d rho times sinh tau plus rho times cosh tau d tau. Dx is d rho cosh tau plus rho sinh tau d tau, and so forth. Dy is d xi, and dz is d zeta. And now we plug that into the line element in Minkowski coordinates. So we have minus dt squared. So that would be minus d rho sinh tau plus rho cosh tau d tau squared plus dx squared. So I won't write all of this out. Plus dy squared is dc squared plus dz squared is d zeta squared. All right, if you now multiply this out and collect terms and use the trig identity cosh squared minus, or the hyperbolic identity, cosh squared minus sinh squared is 1. You'll find the following line element. It's minus rho squared d tau squared plus d rho squared plus d xi squared plus d zeta squared. So this is the line element for flat space-time, the space-time of special relativity, but in Rendler coordinates. It describes the same geometry as the line element for flat space-time in Minkowski coordinates. So now let's examine the properties of flat space-time, the space-time of special relativity. The line element in Minkowski coordinates is minus dt squared plus dx squared plus dy squared plus dz squared. Let's make our life as simple as possible by dropping two of the dimensions. So we'll drop these dimensions and just consider the two-dimensional space-time defined by this line element, minus dt squared plus dx squared. So this is two-dimensional flat space-time. And what this line element is telling us, it's telling us the space-like or time-like or null separation between two nearby events one event at location t comma x, the other event at t plus dt and x plus dx. Okay, and again I remind you, this is the space-time of special relativity. In this case, two-dimensional. So let's look at the following two events. Event 1 is given by t equal 10, x equal 20, and event 2 it has coordinates t equal 13, x equal 25. Let me draw these events on a space-time diagram. So t equal 13, t equal 10, x equal 20 is, say, right here. And t equal 13, a little bit more up the t-axis, and 5 more units along the x direction. So here's event 1, and here's event 2. Before I go on, let me make a remark about this diagram. This is referred to as a space-time diagram, and it's just a plot of the points in the space-time of the coordinates t and x. So each point in this diagram refers to an event in the space-time. But be careful, don't try to assume that this diagram tells us anything about the geometry of the space-time. The geometry must be inferred from the line element. So for example, I've drawn these two coordinate axes. It looks like at right angles here, 90 degrees, but that's just my assuming that the geometry of this piece of paper has something to do with the space-time geometry, and it doesn't. So let me erase that. So there's no meaning ascribed to the fact that I've drawn these coordinate axes in any particular way. Okay, just remember, all of the geometry should be deduced from the line element and not inferred from the way that the picture is drawn on the piece of paper. Okay, so let's work out the separation between these two events. Okay, the line element is minus dt squared. So that's minus, the change in t is 13 minus 10 squared, plus dx squared is 25 minus 20 squared. So that's minus 3 squared is 9, plus 5 squared is 25. So the answer here for ds squared is 16. So what does that tell us? First of all, since ds squared is positive, it tells us that these two events are space-like separated. And then the square root of ds squared, which is 4, tells us that the separation between the events is 4 meters, as seen by an observer who observes these two events as occurring simultaneously. 4 meters or whatever units you choose, as seen by observers who see the events as occurring at the same time. Okay, which observers are these that see these events as occurring at the same time? All right, well, before I answer that, let me back up and answer a more basic question. All right, let's consider an observer and this is the world line of the observer, the path the observer follows through space-time. And here's an event. What time does this observer ascribe to this event? So the observer is carrying a clock, and each time the clock ticks, that's an event. So there's tick number 1, 2, 3, and so forth. These are the clock tick events. So another way of asking this question is, which of these clock tick events does the observer say happens at the same time as this event out here? All right, and the way the observer determines that is the following. The observer sends out a light ray and lets that light ray reflect off of this event and come back. Okay, now let's call this tick event event A and this tick event event B. Right? The observer finds the time interval from A to B and then reasons as follows. Light always travels at the speed of light, so it travels at speed c going out, it travels at speed c coming back. All right, so it takes exactly as much time for the light ray to go out to this event as it does to come back. Therefore, the time of this event is exactly halfway between A and B. Let's call this event E. The time of event E is halfway between A and B. So it looks like on this diagram that this event is simultaneous with event about halfway between these two ticks. Right about there. Now one thing you might wonder about this construction is, how does this observer know to send out this light ray that will intercept this event? How does he know when to send it out? And it doesn't really matter. This observer can send out lots of light rays, and most of them will miss the event. But he simply ignores all those light rays that miss the event and considers only the one that does. And he can also use a helper, a friend, to hold up a mirror at this event and reflect the light ray. One other observation about this diagram that I want to make, and that is, you'll notice that I've drawn or tried to draw these light rays as angles of about 45 degrees in the diagram. And that's because, remember, light rays are null. Light rays are null, meaning they connect events that are light-like separated. Okay, so light separated means ds squared is 0. So in our flat two-dimensional space-time and Minkowski coordinates, that's minus dt squared plus dx squared, which tells us that dt squared divided by dx squared is 1, or in other words, dt divided by dx is plus or minus 1. So this tells us that the light rays travel with slope equal to plus or minus 1, which is 45 degrees. Let's take a closer look at this construction. So let me draw another space-time diagram. So this is the x-axis, the t-axis, and let me consider an observer who, for convenience, passes right through the origin. So this is the world line of the observer, and let's say he follows a path x equal v times t, where v is constant. Now the question I want to ask is, what events in space-time does this observer say are simultaneous with this event right here, the event where the observer passes through the origin? Which events are simultaneous with the origin event? All right, so here is a generic event. Let's give it coordinates t prime, x prime, and recall the construction of how this observer assigns a time to this event. The observer sends out a light ray, which travels at 45 degrees in this diagram, lets it reflect off of that event and return, and then the observer checks the clock time on his clock of the sending event and the receiving event, and then takes the mean, the halfway point between those two events, and that's how he assigns a time. So let's take a look at this mathematically. And by the way, let's refer to this as event A. So this event has coordinates t, a, x, a. And this is event B with coordinates t, b, x, b. All right, this line has slope plus 1, and the slope of this line is given by t prime minus ta divided by x prime minus xa. So that's equal to 1. This line has slope minus 1. It's given by t prime minus tb divided by x prime minus xb. That's minus 1. Now we can use the fact that the events A and B lie along this line, x equal vt. So we can write this, we can replace xa with v times ta. And likewise here we can replace xb with v times tb. Now let me solve these two equations for ta and tb. So first of all, this one we can simplify as the right-hand side is x prime minus vta, and now moving all of the terms involving ta to the same side. This is 1 minus v times ta. So ta is equal to t prime minus x prime divided by 1 minus v. And likewise, for this equation, we have t prime minus tb is equal to minus x prime plus v times tb, or t prime plus x prime is equal to 1 plus v times tb. So that gives us tb equals t prime plus x prime divided by 1 plus v. Okay, and now the time that the observer assigns to this event at t prime x prime is the mean of ta and tb. So that's 1/2 ta plus tb, which is 1/2 t prime minus x prime over 1 minus v plus t prime plus x prime divided by 1 plus v. And we want that to equal 0 because we're asking for the events t prime comma x prime that are simultaneous with the origin event. So we'll set this equal to 0. All right, now solving for x prime as a function of t prime. How do we do that? Well, let's write this as, we can drop the 1/2 because it's set equal to 0. And we'll move this term to the right-hand side. And now cross multiply. We have t prime minus x prime times 1 minus v equals minus t prime plus x prime times 1. Sorry, this should be 1 plus v, and this is 1 minus v. Okay, expanding that out, we have t prime minus x prime plus vt prime minus vx prime equals minus t prime minus x prime plus vt prime plus vx prime. Okay, now some of these factors will cancel. We have a minus x prime here and a minus x prime here. We have a vt prime here and here. And so we're left with 2t prime equals 2vx prime. Of course, the 2's can cancel, and we find x prime is equal to 1 over v times t prime. Okay, remember the world line of the observer was x equal vt. So we can see that for an observer moving along this world line with velocity v, that observer sees the events that are simultaneous with the origin as being events that lie along a line with slope 1 over v. Let me draw this on a space-time diagram. So here are the xt coordinate axes. Here's our observer passing through the origin, and this observer sees the events that lie along this line as all being simultaneous with the origin and with each other. So whatever time this observer reads on his clock at this event, that observer assigns the same time to all the events along this red curve here. And of course, there's nothing special about the origin. The observer assigns the same time to all of these events and these events. So these curves that are viewed as simultaneous for this observer all lie along lines with slope equal to 1 over v. And of course, we can consider observers that don't pass through the origin. It's the same story. If we have an observer traveling like this, that observer would see events simultaneous with this event as lying along a line like this, events simultaneous with this one, and so forth. Now, if we have another observer who's moving, say, along a world line like this, for this observer, 1 over the slope for this observer, those lines are tilted like this. All right, so clearly two events, for example, event here and an event here, that are viewed as simultaneous by this observer on the left are not viewed as simultaneous by the observer on the right. The observer on the right would see these two green dot events as being at distinctly different times. And that's just what we know from special relativity, that the notion of simultaneity is relative. It depends on the observer. So let's return to our example of the two events, event 1, event 2, with coordinates t equal 10, x equal 20 for event 1, and t equal 13, x equal 25 for event 2. We determined before that ds squared is positive for these two events, so they're spacelike separated, and the separation is 4, meaning for any observer that sees these events as simultaneous, they'll measure the distance between these events as being 4 meters. So on a space-time diagram, these events look something like here and here. And now we can ask, which observers see these events as simultaneous? Well, to determine that, we just need to compute the slope between these two events. That's the change in x divided by the change in t. That's 5/3. So the answer is any observer moving along a world line in this diagram with slope 3/5, the inverse of this, will see those events as simultaneous. So all of these observers have slope 3/5, and they all see these two events as occurring at the same time, separated by 4 meters. So now let's look at an example of two events that are time-like related in our two-dimensional flat space-time. So we'll take event 1 to be t equal 10, x equal 20, and event 2 to be t equals 15, x equal 23. Okay, on our space-time diagram, these events look something like this. Okay, the line element in this case is minus dt squared, that's 15 minus 10 squared, plus dx squared, that's 23 minus 20 squared. So this is minus 5 squared is 25, 3 squared is 9, so that's minus 16. So we define, in this case, the events are time-like related. So we define d tau squared to be minus ds squared. Okay, so that would be 16, and d tau is the square root of 16 is 4. So that means that for an observer who sees these two events as occurring at the same spatial location, these events are separated by a time of 4 meters or 4 seconds, whatever units you're using for time. So which observers see these two events as occurring at the same spatial location or same distance from him or her? The same distance or spatial location. All right, I think it's pretty obvious that one observer that sees these events as occurring at the same distance from him or her would be the observer traveling along a world line that passes right through those events. Okay, for that observer, both of those events occur right at the observer's origin, right where the observer is located. It's also probably pretty obvious that other observers that see these events as the same distance from the observer would be observers that are traveling along, well, parallel lines in this diagram, but these are observers who are at rest with respect to the observer that passes right through the event. Okay, so this brings up the more basic question: how does an observer assign a spatial distance to an event? Okay, well, here again is a space-time diagram. Here's an observer, and here's an event. The way the observer assigns a distance to the event is a similar construction to assigning a time. The observer sends out light rays that travel at 45 degrees in this diagram, and this is the light ray that happens to strike the event and reflect off and is reflected back to the observer. Okay, so the event at which this light was emitted is event A, this is event B, and this is our event E. Well, this observer reasons as follows. The time between event A and B is something that he or she can measure on their clock, and that, let's just call that capital T. And that, of course, is the proper time between those events. It's the time as measured by this observer for which those events are the same spatial location. Now, the light ray travels out at speed c and comes back at speed c. So the total distance traveled by the light is t over c. So this event must be half of that distance. So in other words, 1/2 t over c. And this is how the observer assigns a distance to the event. And if you look at this diagram for our two events here and here, does this observer, say the one on the left, assign the same distance to this event as to this event? And the answer is yes. The distance to this event is obtained by sending out light rays, measuring the time between these two events, dividing by c and dividing by 2. And similarly for this event, sending out light rays, looking at the time interval, dividing by c and dividing by 2. And so the question really is it obvious that this time interval, this proper time interval here, is the same as this proper time interval here? Are these the same t's? And the answer is yes. It really comes from the fact that we're working in a simple, flat, two-dimensional space-time in Minkowski coordinates. And that line element only depends on dt and dx. It doesn't depend on t and x directly. So the proper time interval only depends on the changes in t and changes in x. So we can translate this interval, slide it along this line up to here, and it doesn't change dt or dx. So those proper times are indeed the same. And from that, this observer, you can see that observer will infer that the distances for these events are the same as each other. So let me summarize this lecture. If ds squared is positive, then the events are space-like related. and ds is the proper distance between events. So that's the distance as seen by an observer for whom the events are simultaneous. These are space-like related events. Okay, if ds squared is negative, then we define d tau to be the square root of minus ds squared, and this is referred to as the proper time between events. And it's the time interval as measured by an observer for whom the events both occur at the same spatial distance as one another. Okay, these are time-like related events. Okay, and then the remaining case is when ds squared is 0, and this is the case in which the two events are light-like related. Or null, and those are events that can be connected by a light ray. It's worth emphasizing that the line element in general defines the space-like or time-like or null separation between events that are infinitesimally close to one another. It applies to events that are infinitesimally close. Now it's curious, in the examples I've given in this lecture, I haven't worried about the events being infinitesimally close. And I was able to get away with that because we were using the very simple example of flat space-time and Minkowski coordinates. And for this space-time, it has the nice property that the line element doesn't depend on t and x at all. So in other words, in the space-time diagrams, the properties, the geometrical properties of the space-time are the same at every point. It only depends on changes in t and changes in x, not on absolute values of t and x. So in a general curved space-time, these notions like the distance to an event or the time between events become ambiguous. So for example, here's our observer, and here's the event that's far away. The observer can send out light rays, but the properties of the space-time can change from this region to this region. So this argument that it takes the same amount of time for a light ray to travel out as it does to travel back, that no longer necessarily holds in a curved space-time. So things like distances and time intervals become ambiguous whenever these distances are large. But it turns out that as long as we're talking about events within a local region nearby the observer, the line element can always be approximated by the line element for flat space-time in Minkowski coordinates. So within a region near some event that's close to this observer, we can approximate the line element as looking like this flat space-time line element, and within that small region, light rays travel at 45 degrees, and the observer can use the same constructions we use in flat space-time to measure the distance to this event or to measure the time interval between these two nearby events. All right, so in general, the notions of the distance to an event or the time interval between two events, that's ambiguous in a curved space-time unless the two events are very closely are infinitesimally separated. But one thing that doesn't remain ambiguous when we go to curved space-time is the notion of spacelike and timelike separations. So here's some event, and here are light rays traveling out from this event, and they may not travel at 45 degrees, but that's okay. They still separate this space-time in this two-dimensional example into 4 different regions. In this region, in the upper V region, this is referred to as the future of this event. So any event in here is time-like related to this event and in the future of the event. Any event down here in this region is also time-like related to this event and in its past. And what we mean by future and past is any observer will see this event as occurring after this event. Any observer will see this event as occurring before this event. Events that are out here in the other regions are space-like separated with respect to this event. Now, the key property of space-like separated events is that they can have no causal influence over one another. So in particular, whatever happens at this event, it can't have any influence on this event. And the reason is because nothing travels faster than the speed of light. So no information can travel in this diagram from this event to this event. Information can only travel within this future wedge that's bounded by these light rays. So the only events that this event can influence are the events in the future, like this one or this one or this one. And similarly, the only events that can have an influence on this event are events in its past, events in this lower section. Events that are out here, not in the future or the past, they're referred to as space-like separated from this event, and there can be no causal connection between those events.